what I wanted to do was to do some more stuff on invariant points. And I think I've given you a bit of a longer kind of page to do this. Now, are we going to do the whole thing? Yeah, it looks like we're going to have to do the whole thing. Describe fully the single geometrical transformation U represented by the matrix A. So this is one actually we're not going to be so good at doing this because it involves solving trig equations, and that's basically what I was just discussing with you, how we're not going to be so good at that yet because we haven't had a chance to do it. But there was a different way that we can actually learn about drawing these, there we go, giving it away, doing these questions. You could actually draw like the I hat and the j hat like we've got there. So if we just really quickly do this first part, we can't do this as well as I would want to. The I hat is -1/2 and √3/2 upwards. So this is where I has ended up. So this is -1/2, or just a half I should say because it's going to the left. And √3/2 upwards. So if I wanted to find out, this is where I hat was, and it's rotated, because it looks like it's going to be a rotation. I would want to find out what some of those angles were. How could I find out what this angle here is? Of what? Opposite over adjacent. So that's √3/2 divided by 1/2. What is √3/2 divided by 1/2? 2 √3/2, which is just √3. So the inverse tan of √3 is 60. So the inverse tan of √3 is 60. So this angle here is 60. So it looks like the rotation is 120. Now that's what it is for the I hat. We should probably check that it's the same for j hat. So j hat was here, and it's now going -3√2 -1/2. So we've got √3/2 here and 1/2 here. It looks like it's done another rotation as well. If we find out what that angle there is, this time the theta is the inverse tan of that one divided by that one, which ends up as just being 1/√3, which luckily ends up as being 30. So that's 30, and that's 90. So the rotation indeed looks like they've both rotated 120 degrees. So rotation 120 degrees, about 0, 0. Probably should have said anti-clockwise as well, but that's just generally the way that we would say that.
Could they have been like enlarged as well?
Exactly, that's what I was about to say. They could have been enlarged as well. So what would you need to check? Good, the modulus. You want to check the length of this. So you want to check √3/2 squared plus 1/2 squared square rooted. But you can do that without a calculator, guys. √3/2 squared is what? 3/4. What's 1/2 squared? 1/4. What's 3/4 plus 1/4? 1. Square root 1, you get 1. So this is just a rotation here. Now, you'll probably remember from earlier on that I think the rotation matrix is cos theta minus sine theta, cos theta. I don't know if I've remembered that right, though. Yeah? So the reason I did it with the drawing is because actually what we're trying to say here is cos theta is -1/2 and sine theta is √3/2. And you can see that by checking it with the other ones. And if you put that in your calculator wouldn't necessarily give you 120 for both of them. It might give you one of them as 120, and it might give you the other one as, I can't think of what it should be now off the top of my head, but that's because the calculator is going to be giving you the closest one to the origin for both of them. It won't necessarily be giving you the one that's over at 120 degrees where they both have that value, okay? So that's why it's better to draw the diagram until we get really good at solving trig, which we just won't be doing for a couple of months in regular maths, okay? But you can still think about it if you want to and try out these things on your calculators. So transformation V represented by the 2 by 2 matrix B is a reflection in the line y equals x. Right, let's try and construct that. Or do you think we can do that without a diagram? I don't know if I can. No, I can't. I can't. I can't be bothered to change the colours all the time. I and j, y equals x. So where does I go? Y equals minus x. Good. Well, good job I drew y equals minus x anyway. I got lucky. I said, no, I got lucky. I thought it was y equals x and I drew the wrong one, so I still got it. Where should I go? And j? Okay, so now we can actually come up with the matrix. What's it going to be for this bit? Okay, so we've got that bit here. Now, U followed by V is transformation T, which is represented by C. So C is going to be equal to, which one is going to be in the multiplication first?
V.
Yeah, V, which is the matrix B. It's kind of annoying how they say all of these things.
Transformation V.
So yeah, it's transformation V. So C is going to be equal to BA, which is 0 minus 1 minus 1, 0. A half minus root 3 over 2, root 3 over 2, minus a half, which is minus root 3 over 2, plus a half, and root 3 over 2. So that's just all stuff that we needed before. Actually, we did need to do this whole thing. Okay. Now we get to the new part of this question, which is an invariant point. This is why I kind of put this question in here for an invariant point that we've got. For D, it says, show that there is a real number k for which the point 1k is invariant under T. Now remember, T is the matrix C. So if I do this matrix, which is minus root 3 over 2, a half, root 3 over 2, if I apply that to 1k, I should get?
A multiple of 1k.
No, not a multiple of 1k. Exactly 1k, because the point is invariant. It's not an invariant line. It's saying that point is not allowed to move at all, okay? So let me get my page extender on that we get to down here. Okay, so we've got to now actually do the multiplications and see what we get. So I get minus root 3 over 2 plus a half k. What's that going to be equal to? 1, yeah, we're just looking at like, this is the top part and we know it's going to be equal to 1, right? So I'm going to say that is equal to 1. Now, I'm going to solve this equation and see what k is, but that's not the end of the question, because I also need to check it's true of the bottom one as well. In fact, why don't I set up the bottom bit too? What does the bottom part multiply out to when you do this times this? A half plus root 3 over 2k equals k. So I'm going to start off by solving this one. So I get a half k equals 1 plus root 3 over 2. So k is equal to 2 plus root 3. And this equation, I have a half plus root 3 over 2k equals k. How do I solve that equation?
Minus over the root 3 root 2.
Good. So I'm going to collect the k's onto one side. And then?
Times by 2.
I can times it by 2. And then?
What I do?
I mean, you can times by 2 if you want to. You didn't have to, but I'm just doing what you say.
Yeah, that doesn't happen. Nah, you meant to. Factorize out the k.
Let's factorize out k.
And then you divide 1 by that.
And you do 1 divided by 2 minus root 3. Oh, no, I wanted it to be 2 plus root 3.
Rationalize it.
Okay, so we can rationalize it or we can put it in our calculator. But what should we do? Rationalize it? It's old school? Okay, fine. So we get 2 plus root 3 over,
2 plus root.
what does that bit change to?
1. It becomes 1. 4 minus 3. 4 minus 3.
4 minus 3, it becomes 1. So k equals 2 plus root 3. So we need to kind of probably well, I don't know, we don't need a conclusion statement because as long as we have checked that it works for both parts of it, then it works for both parts of it. And then it's definitely invariant. I mean, you could technically, if you wanted to, you could do on your calculator minus 3 over root 2 a half root 3 over 2, and you could multiply it by 1, 2 plus root 3. What would your calculator say? 1, 2 plus root 3, because it's invariant. So this is a little, you could check that out on your calculator and see what happened. I'm going to just push on and just do 5 minutes so that I can set you some homework, because I don't want us to, especially with me not here on Friday, I don't want us to spend too long on this topic. So I won't keep you long, okay? So that's just another thing with invariant points. I've tried to show you as many different ways as invariant points because it's the hardest thing on it. They don't have any examples in the textbook, which means they'll probably put it in the exam. So that's why I'm trying to prepare you as much as I possibly can for this, okay? So linear transformations in 3D. Nothing new, apart from this time I've got to use 3 colours of my pen. So let's just really carefully think about what's happening here. It's very, very difficult to see this on the board, okay? Just because of the lights. But what you should be able to see here is we've got these 3 different axes where you have X, Y, and this time we have Z. Have we done anything with 3D stuff before? We did some stuff, we talked about planes, didn't we? We did talk about planes, so this is good. So I've said here, we saw earlier that we could determine the matrix corresponding to a transformation by transforming each of the unit vectors, the axes, and using these as the columns of the matrix, and this works in 3D too. Now I just want to talk to you about what the plane Z equals 0 looks like. Z equals 0 is just saying, as long as you've got 3 coordinates, but the Z one is 0, then that is on the plane, right? So if you see here, there's this do you see this kind of like faint square kind of thing that's here? That is everything where the Z coordinate is 0. Where if you imagine going up this 3D axis here, as soon as you're at this bit, you can move away from it, but you can never go up or down.
Like a floor.
Like a floor, exactly, it's like a floor.
It's like the floor basically.
It's like a floor where Z is the going from the floor to the ceiling, and X and Y is like running along where the boys are sat over there versus where this bit here, they're like the 2 walls, okay? So if we do a reflection in this plane that we've got here, what's going to change? I, J and K, which ones are going to change? K is the only one that's going to change. So K is going to go still just going in the downwards direction. J is still going over here. And I, so that is J, I, and K. So if we want to now set up what this transformation will look like, obviously this is 3D space now, so I need to use a 3x3 matrix. Normal space, what would normal space look like as a matrix? Because remember in 2D it looked like this.
Just one's going.
What do we call that? One's going down the... Good, you get the identity. I hat, J hat, K hat. Going 1 in the I direction, 1 in the J direction, 1 in the K direction. Well, we just said I and J aren't going to change. I hat hasn't changed when it's a reflection. J hat hasn't changed. K hat has changed. So this represents things as a reflection in the plane Z equals 0, right?
So it won't be lines more, will it?
No.
It will be plane.
It will be because you can't really reflect in a line.
Yeah, would that happen?
You won't have diagonal planes to do reflections in.
Z equal to y.
But you will have rotations. Okay? You will have rotations. Now, the rotations is the last thing that I really want to show you. By the way, I've shown you the reflection in the plane Z equals 0. I can't show you all the reflections. They might do other ones and stuff as well. I'm just showing you one as an example and how you would build that up. You recognize that something has changed in the K direction. So we're going to think about doing some rotations. Now, these look just the same as the rotation matrices that you have for 2 dimensions, but there's a slight twist on them as well, and I'll just go through what that looks like. So if we're going to rotate by an angle theta about the y-axis, this time it's rotating it. I mean, this is the thing that I'm confused about, because this is in the textbook as well. It says the rotation is anti-clockwise relative to the positive y-axis. But if this is the positive y-axis, and I'm looking at it in this direction, as far as I'm concerned, that looks like it's going clockwise. But the textbook says this, and this is exactly the formula that the textbook uses. So I'm just confused about why it says anti-clockwise. It works for x and z, but this one is kind of weird. But these are the formula that we should be using. I think it might be meaning looking at the other way. Yes, but I'll help you. I'll help you memorize them in a second, okay? So just as a reminder, this arrow has moved, but it's just rotated a little bit. The y part hasn't changed at all, and the x part has changed. Do you remember how we just were saying, like, these bits here, this one would be, because this is a hypotenuse, this one is adjacent, so it would be cos theta. This one is opposite, so it would be sine theta. So that's why it's going sine theta in the I direction, nothing in the j direction, and it's now going cos theta upwards in the k direction. The y part hasn't changed, so it's just 0, 1, 0. And the k part, this running along here is cos theta, this running along here is sine theta, but it's a minus sine theta because it's going down in the k direction that we've got there. So I hat is this one, so you get cos 0 minus sine. J hat hasn't changed because it's rotating about its own axis, and k hat is sine theta 0 cos theta because it's of that rotation that it's done there. So this is what it would be if it was a rotation about the x-axis. Look, you can tell it's a rotation about the x-axis because you've got that thing that you've got there. And then if you look about this sub-matrix that we've got here, this is the same rotation matrix that you have in 2 dimensions, where you have cos, cos, sine, minus sine. For the y-axis is the one we've just dealt with, and for the z-axis, again, the z-axis has not rotated, and you've got your cos, cos, sine, minus sine. Now this is why I'm just a little bit at odds with the book, because I think that should be a minus sign and that should be a plus sign, and we should have rotated it going in the other direction instead. However, there have been exam questions that use it in the way that I've got it written here, so I want us to just learn it in this particular way. Ishak?
Could be like the sort of the arrow on the x is like when that turns, then sort of Z1 like rotates to sort of like support that change.
It is. I just get it's the directions of them that's a little bit confusing with how it's all put together.
You know, when it says relative to the positive y-axis, does that mean you look at it from the positive side?
But then when these ones are constructed, I've checked both of these out, you look at them in the way that I expect you to look at them. That's why there's a bit of a weird mismatch about this. So if I can get to the bottom of this, I might even have to email Edexcel and be like, why is this one different? And I will obviously explain it to you. But you've got this page here. Most of all, we can see that you can actually see how these are formed. The only one that's different is this, the y-axis, where they switch around. Okay, I will do a very, very, very quick example on this, and then we're going to go away. Going to go and do this straight away. Okay. So for this question that we've got, we want to describe this transformation represented by M. Can anybody spot what it's going to? It's a rotation about the y-axis, because we can see this column that we've got here, okay? Yeah, and this is then really similar, because we can see this is what cos theta is.
But the minus is the other way.
I know, this is why I hate this. And then we've got that sine theta is a half, because of the way it's the minuses are the other way. Now, we can either sketch this to draw and see what it would look like, or we can try this one by solving trig. This one will work by solving trig because they're just both the positive values that you've got here. So if you do the inverse cos of root 3 over 2, and if you do the inverse sine of a half, if you get the same value of theta, then it's just completely fine. It's just if your calculator gives you a different value of theta. These are ones eventually you'll know from the top of your head. What is the inverse sine of a half? I'll save you some time. It's 30. And the inverse cos of root 3 over 2 is also 30. So because they match, we didn't need to do that drawing. However, we could have done that drawing. I could have drawn the cosine of theta is root 3 over 2. Remember, cosine is running along the bottom. The sine of theta is a half. And you can see that one is going in the positive direction. That one is going in the positive direction. This is to do with the unit circle I showed you earlier. Hypotenuse is 1. Theta is the inverse tan of that divided by that, which does give you 30 degrees as well. But really, this is me just wanting to touch on some of these ideas that we have. So we've got that it's a rotation about the y-axis, 30 degrees. Nearly there. Part B, find the image of the point with coordinates -1, -2, 1 under the transformation represented by m. What do you think we need to do with -1, -2, 1?
Multiply it by the image.
Good. You're just going to put on your calculator because I've run out of energy. You're going to do this, 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 this. You're going to multiply it by -1, 2, -2, sorry, 1. And you're going to get a coordinate of 3 different points that we've got here. Shall I do this in my head?
No.
Yeah, I'm going to do it in my head. So we've got that. So it's 1 minus root 3 over 2. We've then got that. So we've got -2, and then I've got a half. I've got 1 plus root 3 over 2. So the image of the point is going to be 1 minus root 3 over 2, -2, 1 plus root 3 over 2. And then I can set you a few questions from 7E to have a go at there.